Okay, there it is. Okay, got it. Phew. All right, success. So today we're going to talk about trustworthy, controllable, and fair, not displays, but AI. I am at thank you very much for the introduction. I'm professor in computer vision and human sensing in Queen Mary University of London, and heading the Center for Multimodal AI there. So just a little bit of a short introduction about what I'm doing so that you understand a little bit where I'm coming from. My general research is in the area of multimodal machine learning. In particular, work on computer vision, machine learning, and pattern recognition methodologies. Primarily have been used them in order to interpret and analyze multimodal human signals. So we worked a lot of facial expression recognition, emotion recognition from images, from videos, but also from brain and physiological signals. Worked a lot on some fundamental problems in machine learning. So used self-supervised learning, learning with noisy labels, unlearning, LLM alignment and control, uncertainty estimation, and recently on generation, so generation of images and video. Today I'm going to talk a little bit more on three of those. I picked up some works from these areas, and I'm going to focus on three aspects. So the first thing is I'm going to be talking about how to teach AI systems to know what they know and how well they know it. Okay. So the idea is that we have systems that not only give answers, but they give estimates about how uncertain they are about the answers that they are giving. Estimates of uncertainty in the output. That's the first theme. The second is how to control or align AI. This is a major, but I think one of the major challenges that we face that we will face in the next years, and particularly important as AI is becoming more and more powerful. So I'm going to talk a little bit about controllable and aligned generation of text and images. So in the intersection of vision and language models. And the final thing that I will be talking about is about fairness and bias. I'm going to talk about anonymization, similar to the previous one of the previous talks. And I'm going to talk also a little bit about biases. So the first thing I'm going to talk about is uncertainty. And I'm going to talk about uncertainty in a specific domain. It is the domain of affect analysis. Okay. The motivation, it comes into the first part of the talk. So how we have systems that not only give an answer, but giving an input, giving the output a prediction about, for example, about the affect or about the emotional state of the person that it is depicted in it, but also that they are able to give a prediction about how certain they are about their estimation, about their estimate. The motivation for this work was a little bit different. We started from a different perspective. The perspective where we started was as follows. So traditionally what you did have in this kind of systems of affect analysis, you have pairs of, in a supervised learning framework, you have pairs of inputs and outputs, and you train in a supervised manner so that when you get a new input that you will have the output. And the output can be, for example, in the arousal valence space. Arousal is how excited somebody is. Valence, how positive or negative the emotion is. It is a continuous space. So it is a number. However, one of the problems that we had was that in several cases, and especially for faces that were a little bit ambiguous in the displayed emotion, even between annotators that would annotate these datasets, you would have differences. So in several of those situations, what you do is that you take as ground truth to be the middle, so the mean of the different annotation. However, this paradigm, this way of dealing with the data is a kind of an, how do you say that, like a shortcut. It avoids the signal that it is there, which means that there is some uncertainty in even how humans evaluate judge the input. And there is, and this kind of uncertainty, this kind of ambiguity is seen in case that we have multiple annotations or even self-reporting. And the reason is that there are different reasons. So you have different cultural reasons, you have variation depending on the gender, on the age, on the experiences, on the context. Even if you say as well, how do you feel or how you felt at that specific time instance in a specific situation, you might be giving very different answers. So what we do in this case is expanding the current supervised framework in the following way. So as I said, in the current supervised, in the normal, let's say, supervised training, what you have is pairs of inputs, and you have a ground truth, which is and a ground truth which is a continuous value. Let's consider this case. Now, in this work, what we consider is as follows. We will not consider this ground truth as the absolute ground truth, but we are going to consider that the real ground truth is actually somewhere around. Okay, and we will model the uncertainty about where exactly the ground truth should be with the variance of a Gaussian that we are going to place it around the label that we have in our dataset. And now what we are going to do is that we are going to train a system in the following way. We are going to train the system so that given an input, it will try to estimate, to try to predict the mean of the Gaussian, but it is also trying to predict also, to give an estimate about the uncertainty. So we're going to have two quantities now. One is the mean and the other one is the uncertainty. And then during test time then, the system would be able to give an estimate about the affect, or in general the quantity that we are interested in, and about the uncertainty. And we are getting now one specific loss that we are introducing. We are training the system without having as annotations only those means, and treating the variance as an unknown quantity. And during test time, then we are able to predict it as well. If you have any question on the technical details, I can ask now, or we can address it later. But in this, I'm going to get a little bit into some of the results here. So we try to evaluate whether this uncertainty that we are estimating, so this variance that we are estimating, whether it is useful or not, whether it makes sense or not. And in some of the datasets that we have, in specific dataset, which is the Amigos dataset, we have annotations of different, we have several annotations of multiple annotators. And here we can see, basically on the different scales on the arousal valence, we can see the agreement, the correlation between the annotations of the different annotators. So you see that, well, along the diagonal we have high values and lower values across the diagonal. Now, for some of the samples, you have good agreement, so they agree about the annotators agree. In some of the samples, they have also variance themselves. So what we do here is that what we do here is we estimate the correlation between the variance that we are estimating and the variance that between the annotators. And we can see that we have positive correlations both for the arousal and the valence, which means that for the samples that the annotators disagree, we calculate a higher variance, which means that we are deeming them, we are saying that these are uncertain. And we can see in another dataset now, which is the AffectNet dataset, we are again trying to see whether the estimates of the uncertainty that we have, so the variance, whether it is useful or not. There we do not have multiple annotators. However, there we have the following setting. So we have an estimation, so we have an annotation in terms of the arousal and valence, so we have a continuous value, but we have also a categorical annotation of the sample into one of the categories of emotional categories. So, according to a certain scheme of Ekman, the specific, the categorical emotions, they lie on specific areas in the arousal and valence plot. Now, whenever we have disagreement between the arousal and valence values and the categorical label, we deem those, we say that these are noisy samples, okay? We do not use this information during training, but what we want to do is we want to see whether the estimates that we have for the samples, for the variance, for the samples that we deem difficult, that we deem noisy, whether it is higher than the variance that we estimate for the samples on where there is agreement between the categorical labels and the arousal and valence labels. And actually we see that very clearly. So you see the distributions here, where you see the two different peaks. On the left-hand side, we see that for not noisy samples, we have lower variances. For noisy samples, we see that we have higher variances. And not only that, but we can see also that using this variance as using this network that estimates the variance except in addition to the affect, also gives an improvement in the results in terms of the original problem that we try to address, so arousal valence estimation. Okay? All right. Until when do I have time? Is this, when do I need to end? 12:35. 12:35, okay, good. Just that I have an idea. All right. The second work that I want to present now is in the same general category. So we want to have a model that is giving confidences about its outputs. We are going to do that now in the domain of large language models. This is under review. I hope it will be accepted. Otherwise, yeah, well. Good. Now, what are the current methodologies for doing this kind of confidence estimation in the domain of large language models? So there is one general category of methodologies which are post hoc methods. So you have a model that you're asking a question, it gives an answer, and then you have a second stage in which another system, a calibrator, is taking the question, is taking the answer of the model. It may be investigating, have access also to the internal states of the LLM that produced the answer, but then it gives the confidence. This can be calibrated, but it is slow. So what do I mean when I say calibrated? I didn't say what I mean when I say calibrated. Calibrated means that you give a number that quantifies the confidence. However, this number needs to correspond to something. Typically, this number, so a useful thing for this number is to correspond to be linearly, to very linearly with the accuracy of the answer. And the accuracy can be calculated differently in different domains. If it is linearly corresponds to the value that we are interested in the accuracy, for example, then we say that it is calibrated. Okay, so these methods can be calibrated, but it is maybe a little bit, they are slow. The other one is to ask the system, ask the model itself to give not only the answer, but to give also a confidence in a verbal manner. So you can train it in order to give answers like this. So to give the answer, but also give the confidence. However, this is typically is not calibrated. And what we want to do now is that we want to have a system, we want to have a model, and this is what our Grace model does, that at the same time is giving, that it is giving the answer, but at the same time, based from some internal states that the model has, to have a way of calculating a quantity, a number, that gives the confidence to the answer. And I'm going to tell you a little bit exactly how we do that. But what I want to say is that, first of all, it does so without having to do anything post hoc, without adding any computational constraint, any computational, any additional computational cost. Okay, that's the first thing. And the second is that it is well calibrated. And here we see the calibration error between the post hoc methods, our methods, and the verbalized responses. Okay, so the lower the better. So how do we do it? How do we do it is in the following way. So how we do it is that, well, the LLMs, they have a vocabulary, they have a token, they have a number of tokens that they can produce. What we do is that we take a pre-trained LLM, but what we do is that we teach it in order to produce another token. So we we augment the token space, and we have an additional token. Now, so since the vocabulary has increased, then the model at some point will be able to produce this special token. Now, what we are doing then is that this token will have a certain probability when it is emitted. What we want to do is that we will align the probability of having this token with a calibration target using an MSE loss, and then we train the model using a supervised fine-tuning manner. So, how we do that? Maybe I have to say a little bit how we do that. In order to do that, then we need to make a data set in which we have questions, answers. In the end, we will add the special token, and we want to have a ground truth now probability. So this probability that it is calibrated, and that it is so that we can align it with the ground truth that we will have. So the question is, how do we produce such a data set? So how we produce such a data set is in the following. We produce it in the following way. So we have a data set of questions and answers with ground truth. This is for several problems for several large problems in which large language models have been trained on. So we have these pairs. We train the model to. We have the model. The model is producing the answer. We can calculate now the basically what we can do is that we add in the desired answer, we add the special token in the end, so that the model learns to produce the special token at the end of its reply. And because we have now the answer, then we can calculate also the accuracy of the answer. We can calculate the accuracy of the answer, and then and then what we do is that we align the probability of this. We align the probability with the ground truth that it is estimated based on the answer that the LLM has given. That is basically it. And during test time, the only thing that we need to do is that, well, basically we see whether the model, given a certain question, it produces the answer. It gives the special token in the end, because this is how it has been trained. And based on the probability of it, we consider actually the probability of it, we consider it to be the confidence that we have for to the answer. Now, how can we use now this confidence? First of all, we can use it as we can consider that this is the end product that we want to that we want. For example, a user can interpret the confidence, and then based on the confidence, if it is high enough, then he can or she can decide whether the answer is useful for them or not. In this specific, we are displaying here two possible applications of it for test time scaling. What do we mean test time scaling? Test time scaling is that in several cases you can have an LLM. Well, test time scaling means the following. It can mean several things, but one of the things that it can mean is this, that you can generate several answers and you have a way of evaluating how good those answers are. You can then pick up the best of the answers. You can combine the answers based on the confidences, based on the scores that you have, and you can do many other things. So in this case, we are considering the confidence as a measure of the quality of the answer. And we are using it in the following way. So the first thing is that we are considering a scheme in which the different answers are weighted, so that you can get a final response. And the other one is that you are so you consider a fixed number of answers, and that you are combining them according to the confidences. So that is the first scheme. And the second is that you are sampling more and more answers until one of the answers have a confidence that it is high enough. Okay? Right, and that's it. And then we can see here that with this diagram, I don't know if we can have all of them, is that we can see that in comparison to other works in the literature, we have a better we have better scores. That is about how good the calibration is, and here is how well it can perform for test time scaling. So this is the number of the answers that we get. So this is with 2, 4, 8, etc., etc. And so you see that the accuracy is increasing by increasing the number of samples. And sometimes actually test time scaling is a very good way of increasing the performance of your system without having to spend a lot of time in the training. So you can see in different domains, how much increase in the performance that you have. And here the second scheme, in which we are sampling until we get to the desired confidence. This is the average number of samples. So here we have 8 times, with increasing 8 times the complexity. Then you see that you have with a 3% improvement. And with the sampling scheme, like with only 2%, then you have comparable increase in the accuracy. I am not going to get a little bit more into these things. I'm going to talk about now a little bit. Yes, okay. So I'm going to talk a little bit about a few other works that we have. Maybe I'll talk a little bit into about the anonymization and the fairness, and if I have time, I will get back into the controllable generation. So maybe I'll skip that a little bit because we started a little bit late. I'm going to talk a little bit about anonymization. We have 3 works there. The first is anonymization, which was presented in CVPR in 2023. It was one of the highlight papers. Well, I don't have to give a lot of motivation around it because thanks to the previous speaker. What I want to say is that the original motivation was to remove the identity but to maintain as many of the attributes that we can from the original phase, because we do not know in advance what is the how we want to use the data. The idea was we have one data set, specifically the motivation was on mental health data set. We have a lot of privacy issue in that domain. Go into take that data set, replace the faces, keep as many of the attributes as possible so that you can train on the synthetic data set. And how do we do? Okay, yes, so we want to preserve the attributes. The key thing was that we do not know which are the attributes that we want to preserve. At that time we worked on GANs, but the main idea is transferable to other domains as well. Let me see. Okay, that's good. Okay, so what we do is that we start with a real data set. Okay. What we want is that we want to create an anonymized data set. How we create an anonymized data set? We have a generator. How does a generator work? It takes as input a latent code. So the idea is that we take we find latent codes so that the images that we generate are as close as possible to the images that we have in the real data set. How we go about it? We start from the real data set. We take an image that we are interested in. Then we go through the inversion and we find the latent code that it is associated to it. Inversion means that you get a latent code such that if you give it to the generator, it will produce exactly the same image. We do not want that because we want to remove the ID. So what do we do is that we are finding a fake image. So we have another fake data set. We find a fake image that it is in the latent space, that it is closer to the real one that we want to replace. Okay. Now what we're going to do is that we are going to combine these latent codes, and then we are going to do some optimization such that with the new latent code that we have, we will produce an image that it is as close as possible to the real image, but without having the same identity. Does it make sense? Okay. So how we do that is that we have, similar to the previous speaker, we have, but a little bit differently, we have two losses. One loss that reflect also what we want to do. So we want to remove the identity. So this is going to be the identity, a loss related to the identity, but we want to preserve the attributes. This is a cost that is going to be related to the attributes. So how we do that is that we have now an encoder here that it is extracts representations from the synthetic and from the real image, and we want this loss that it is related to the attributes to be as small as possible. Okay, and we want that the loss with related to the identity, this is the similarity between the real and the real and the artificial phase. We want it to be at a specific. We want them to be at a specific distance. So we want that it is controllable. This M here is a parameter that controls how similar the faces are. So two things that are important here. One is what is the attribute loss that we have, and the second is what is the face similarity loss. In the attribute loss, we use something that it is general. We didn't want to train it in a supervised manner based on the pose or the expression or anything like that. Why? Because we didn't know in advance what are the downstream applications. Okay, that was the first observation. And the second thing here is that we use the arc face, which is very nice work. And we kept the similarity to a certain distance. And you see here, well, I don't need to show very much in detail, but with the different M's, then you can vary how similar the generated faces are in relation to the original to the original face. Let's move a little bit more. Okay. Now, how did we evaluate? We evaluated now on different attributes. So some attributes that are related to the outer face, some attributes that are related to the inner face. Keep in mind that these attributes, we have detectors for them, we have evaluators for them, but we didn't use them during training. And we compare with different methodologies. We were better than the ones that were at that time. I don't want to say very much in that. The only thing that I want to say perhaps is that competitive methods at that time were very good at outer face attribute. Why? Is it because they were taking and they were cropping the face and then were removing the inner face? But we had competitive performance to them without even having, yes, we have competitive performance to them, either on the inner and on the outer face. Okay, so this is the second thing. How much time I have? So 35, you said? Yeah. Okay. All right. Maybe very briefly, 2 minutes or not? Yes? Okay. Okay. So I'm going to talk a little bit and on a work that we have now in the CVPR 2025. We just presented that. And this is about dealing with the bias, that some models have. So the main idea, what is the main idea here is that when you're training, for example, a classifier to distinguish between smiling and non-smiling face, because the data set is imbalanced, primarily because of that, then what you do is that you have differences between the performance of the classifier on, for example, on some protected attributes, on male and female. What you would want to do is that independent of the protected characteristic, for example, it could be race, it could be gender, it could be religion, it could be all of those things. What you want to do is that you want to have the performance of the system to be as similar as possible with respect to the attribute that you want to estimate. The main idea now is that we want to generate synthetic data so that we augment the data set, so that we reduce this gap, however, without reducing also the performance, the average performance of the system, right? We don't want to get this to the 71. That is not the best. That is not the way. So how do we generate the synthetic data? We generate the synthetic data from a text-to-image model, and we address two problems. The first is that if we have simple prompts, then you do not have a lot of diversity in the images that you generate. So we dealt with this problem by having an LLM that it is generating contextual prompts, considering several other characteristics. So instead of asking portrait face photo of a smiling male, then we are having the ChatGPT generating prompts that will say, generate in that pose with this expression, with this hair, with this, and etc. And these attributes now that we vary are also generated in an automatic manner from the ChatGPT. So we are asking what are the facial attributes that are important, and we can vary without changing the attribute that we are interested in, which is the smile, and then it generates all of those things. So this is the first thing. And the second thing that I wanted to say is that when we generate synthetic data, then we are introducing now two domain shifts. What are two shifts basically? What are the shifts that we are generating? The first thing is that we are generating a shift because we are changing the distribution of the data according to in two ways. One in a desirable way and one in an undesirable way. The desirable way is that we are having more balance between, or we are decreasing the protected characteristic. We are generating more images of a certain ethnicity, for example. Okay, this is something that it is desirable. So we want to improve the fairness. Okay, this is a desirable shift. However, we are introducing also a domain shift between the synthetic images and the real images. The synthetic images are not exactly the same as the real images. Specifically because the datasets that we have, the training dataset, may be different than the dataset on which the text-to-image model has been trained. So what we want to do is that we are going to address this, and to do that in the following way. So what we observe here is that some of the parameters are sensitive to the domain shift, and some of the parameters are more sensitive to the fairness. So what we do is that we are examining, because we can generate the data in a controllable manner, then we can make an unbiased synthetic data. We can generate biased synthetic data that it is following the biases of the real data, and then we can see the differences in the gradient between those three datasets. And we can identify which are the parameters are sensitive to the bias, which parameters are sensitive to the domain shift. And we want to pick up parameters that are sensitive to the bias, okay, sensitive to the biases, and insensitive to the domain. Okay, so we rank them according to the gradients. We pick up the ones that are, we pick up the overlap, and then we are fine-tuning only according to them. And this is a good way, and we are showing some of the results, and if you want to see some more results, you can see in the paper. I will finish now with just one thought, and it will take just 30 seconds. So I'm taking as a given, actually, which is on the security. So I'm taking as a given two things. So first of all, that we are on a path to superintelligence. There is no doubt about that, according to me. Second, that we are having AI that is going to be taking actions in the real world. So either we're going to talk about autonomous systems or agents, software agents that can interact with you, that can but they're going to take decisions, they're going to take actions in the real world. Okay, so these things, if you do not have a way of controlling the AI agent, to me, they are a recipe for a disaster, actually. So there is a very high risk with this. So I really believe that in the that in the next time, an essential, perhaps even the single most important issue that we will face is how we can control and how we can monitor AI systems, how we can monitor the actions that they are taking in the real world, how we are monitoring the decisions that they are making. We need to have AI systems that are going to be taking these decisions. We have a problem of how we're going to do that, and a big problem is going to be how we can measure the long-term outcomes. So the long-term outcomes of their action. So you're taking an action, you're giving an advice. What is the long-term consequences of that? I think that these are the things that are going to be. These are not easy problems, but I think that these are going to be one of the major issues. Actually, maybe the single most important issue in the next years. And that's it. Thank you very much.
Is there anyone who have any questions?
Thank you. Thank you for your talk. For your first two, about the uncertainty and confidence, correct me if I'm wrong. For the very first one, you just assume the prediction is not 1 point, instead is a distribution, yes. And Gaussian distribution, and the variance is just uncertainty. For the second one, you introduce a calibration data set, and you measure the distance between the ground truth and the prediction, and that is a kind of uncertainty. Yes. Okay, so on top of my head, quite straightforward. Can we use the idea from the first work to the second one and vice versa?
For the second, that's what I've been trying to say to my student to do. But so exactly that is what we want to do now for the second paper, and see whether that is not if it is possible. I believe that it is possible, but we need to verify that as well.
Okay.
Yeah, I think that this is something that we will be doing.
Okay, thank you.
Yeah.
Great question. Yeah, I think.
I have a question about the LLM1 as well.
Mm-hmm.
So, in the when measuring uncertainty from the LLM with a calibrator network or with not the calibrator network, with a self-uncertainty, have you measured the uncertainty, the confidence rather, when the model is actually hallucinating? So is it very confidently predicting these hallucinations, or do we see that during the hallucinations we actually have...
So with the results that we have, we see that we have a good correlation between the accuracy of the answer and the confidence score. So when we have a hallucination, then the accuracy is low. Therefore, the answer is that we do have reduced confidence.
Okay.
That's how we evaluate.
Yes, we'll go back to the earlier page. Still about the work,
The which work?
the large language model. Yeah. So I think the calibration data set matters a lot, right? So because I think it's related to conformal predictions, you know.
Conformal predictions also use they use a calibration data set as well. Yes, so they have a validation set there. Yes.
So it seems to me that you are generating a calibration data set based on the large language models you are going to calibrate.
So we are training the model, then we are generating the calibration, then we are generating the calibration data, and then we are training in terms so as to predict this the confidence.
Yeah. So I mean, it's like you are trying to compare a new input. Okay, so you have a new input, you are going to generate a response and also the special
token. Yes.
And you have a calibration data set that include the input, output, and the special token.
And the
So
special
you can
token,
compare
yes.
the new input with the data set and kind of rank the new input, output with the calibration data set and have a confidence score.
To compare it, not to rank it, but yes, to compare. Yeah.
Yes.
Yeah.
But the calibration data set itself is also generated by some large language models. So I mean, it's not a ground truth.
The calibration for the calibration we have ground truth question answers. So we have ground truth question answers on the specific on some specific domains. So and then the accuracy of a given answer by the system is calculated based on existing metrics of the calculate the accuracy. For example, you calculate a certain score, the rule score, for example, or any other score you can calculate there. And that is what is giving you the ground truth target, the ground truth accuracy. So you do not need the dataset. The calibration dataset does not need to have. Is not generated by the model model. It's not artificial.
Okay. Yeah.
Okay.
Thank you.
Yeah, thanks again. Oh, sorry. See.
I have a question about the fairness study, the last one.
Yeah.
So I can see that there are some alternative designs. For instance, why not use a combination of real-world data and synthetic data? Like why purely synthetic data? And another alternative would be like why use diffusion, like prompt-based diffusion instead of like image editing?
So we have a system that we have the real data, and then we add synthetic data. So we have okay. So the system in the end is being trained in a combination of those two. There are other ways on balancing the data set or addressing the fairness. For example, we could go and retrieve in another we could retrieve real data. However, we do not have annotations for the real data. In this case, why did we go from a text to image model and not image editing? We could have done that. The point that what we thought at that point is that if we start from scratch with being very precise on the what we want to generate, then we would have a better control than doing image editing. So in this paper here, which is this paper, it was WACV. We did exactly what you said. So, well, I think what you said. So what we did is that we started with an image, and then we altered it in the way that we wanted. So we did an editing, and we tried to balance the data set in this manner. I didn't describe this work, but yeah, that's the idea. So yeah, there are two ways of doing that. Either you can start from scratch, or you can edit. All of these are viable possibilities.
Okay. Yeah. Thanks for your explanation. Yeah.
Okay, I think we don't have time for more questions, so just that's okay.